Welcome back to the next video about my electronic steering wheel / rudder jog IP68. In the previous two videos we already did a ton of static calculations and bending calculations for the bearing that will hold that wheel. And I promised you in the last video that this time I will show you an initial drawing for the bearing mechanism to hold that wheel. Card here, link in the description. And that's what we will start off with today, with the initial drawing and how I came up with it. We also have to do a few more static calculations. Well, not really static, one static calculations, but a few more calculations for that thing. And this time, I promise you, this will be the last video with just calculations, okay? So, enjoy. And here's the initial drawing. We have here our POM bearing body as we know it. Please note that it shrunk to 65 millimeters and the extension of our bearing that is complying a little bit to take on the edge loading here when we are pulling down on the wheel is a bit longer now, 30 millimeters, and the rest of the body is 35 millimeters. And here's our aluminum shaft inside the bearing. The inside end has a larger diameter, so we can't pull it out. And on the end with the wheel, the business end, there will be a threaded extension that will go through a new hole here at the center of the wheel, and that will be secured with a nut. Then we have our wheel shaft adapter, so with 3 holes here at the outer diameter for the 3 mounting slots here, for also M6 bolts. And I have obviously decided not to use the one I bought with the wheel. That's from for carts, for little racing carts, because I really first don't like that kingpin principle here, and secondly, I can't use a kingpin in my construction. Because there will be a little gap here between the wheel plate, the center plate of the wheel, and the shaft, so we can actually compress everything here with that nut, giving us at least the ability to create some friction in the whole assembly. The moment from the wheel will be transmitted onto the shaft by a little key in here. So we will have a slot in our adapter for that key and a slot in our shaft. And using a key instead of a through kingpin here will allow the whole thing to wiggle a little bit back and forth, allowing us the whole thing with the compressing everything with that nut here. The last feature, we haven't talked about it before, are 2 bolts here. One bolt running here through the end of the shaft and sticking out, and another bolt here sticking out of the bearing housing. And these will obviously collide, so you cannot turn the wheel as many times as you want. You have a plus minus, not quite 180 degree, but plus minus 170 degrees or something. We talked about that in the first part of the video. Card here, link in the description. So, how did I arrive at that drawing with these specific dimensions here? As we learned in the previous 2 videos, there are a lot of conflicting parameters here. For example, if I make my bearing longer, I can reduce the forces on the bearing, but at the same time I increase the bending of the shaft, because then if my bearing is longer, the shaft is longer. So I had to pick from all the tables and calculations we made parameters that would fit overall together. That's not a straightforward process. That's basically trial and error. And I didn't arrive at that solution right away. I actually made three different, or have three different versions here with different stick outs ranging from 55 millimeters to 45 millimeters. That's what you see in the drawing right now. And I did for these three versions all the calculations again and made sure that everything is within the limits we set out for us. For example, here the stick out bending in that version is 0.09 millimeters, so smaller than the 0.1 millimeter we wanted. Here it was 0.12 millimeters, so and in that version it was 0.16 millimeters, so not acceptable. So trial and error. I also had to take into account what I can actually manufacture. And for example, drilling here a hole for a 14 millimeter shaft. That shaft currently is 12 millimeters. It's a little bit too much for my little mill. Also, the length of the hole is limited by the capabilities of my mill to 65 millimeters. So yeah, what can I really manufacture? Okay, so what are these other calculations I want to do in this video, respectively, what parts of my construction I'm concerned about breaking? First, we have that remember there are three holes here in that wheel, M6 bolts that hold on here into a M6 threaded hole in my wheel shaft adapter, plus the extension, also M6 threaded off my shaft with that M6 nut here. Will they break? Will they hold? To do these calculations basically about the strength of threads, we need two more material parameters. We already used the modulus of elasticity and the ball indentation hardness and the compressive strength. Now, these three parameters are non-destructive parameters. That is, they are about either elastic deformation, that is deformation after the applied force is gone, goes back again, or plastic deformation like the ball indentation hardness, that is the force is applied and even if the force is away, the deformation might be still there. But now these two new parameters we need for the threads, the shear strength and the tensile strength, these are destructive limits. So if you go over these limits, something breaks. The shear strength tells you how much shear force a bolt, my black bolt here, can take before it breaks. And that's for 6060 aluminum, 105 megapascals. Remember, megapascals is Newton per square millimeter, meaning if my bolt has here an area of 1 square millimeter, assuming it's a round bolt, then it can take a force up to 105 newtons until it breaks. The tensile strength tells you how much force you need to apply to pull a bolt apart. For our 6060, that's 120 megapascals. So again, if our bolt, wire, has an area of 1 square millimeter, I need 120 newtons to break it when pulling on it. And we're back in an online calculator. This time, it's in German. You can use Google Translate if you want. I put a link in the description for the minimum thread depth for bolts, according to VDI, that's Verein Deutscher Ingenieure, the Association of German Engineers, 2230. And here we first select, the size of our screws, that's bolts, that's M6, and the class, so how much the bolt itself can take. We can use the weakest class here. It doesn't matter because we are only interested in how much the thread in our hole can take, not the bolt itself. And then we have the thread material, and unfortunately my aluminum 6060 is not amongst them, but you can enter here the values of your material, and that's RM, that's the tensile strength, that was 120 megapascals. And then we need the shear strength divided by the tensile strength. And that is 0.875. And then you have a lot more information what's going on here. But to use the maximum strength of the bolt type we choose, we need a depth of 9.3 millimeters. But that's not what we want. Further down here, you can get the same calculations for a reduced force. And simply starting at 1 kilonewton. And then we have here 2.67 millimeters. And then at 2 kilonewtons, we need 3.52 millimeters, and so on and so on. I'll do some calculations and come back with the table to you. Here are the results. So for 100 newtons, I need a thread length of 2.08 millimeters, 200 newtons, 2.16, 500, 2.38, 1000, 2.76, 2000, 3.52, and 5000, 5.78. And you see that's absolutely not linear. That's why I'm using an online calculator, because the math behind it is quite complicated. By the way, M6 nut here has between 3 or 4 windings, let's say 3.5 windings or 3 windings. That would make it a thread length of 3 millimeters, so that falls between 1000 and 2000 newtons. Remember, our pull force was about 15 kilograms on the wheel. And we have to also take into consideration that we torque down the screws a little bit. So let's say for the same amount, so 30 kilograms, about 300 newtons, and then we apply a safety factor of 3, because that's a dynamic force. So our thread needs to take at least 900 newtons. So everything here at the front, the bolts and the threaded extension here of the shaft should be fine. And as long as we keep the length of our threads at or above 3 millimeters, which is easily achievable because the shortest bolts you can get here are 10 millimeters. You have at least 6 millimeters here in the material, and we already talked about that nut here, 3 millimeters thread length. Talking about bolts, what is about the bolts here threaded into the POM body of our bearing? The shear strength and the tensile strength at 55 megapascals, respectively 65 megapascals, are almost only half of that of 6060 aluminum. So let's go back into our online calculator. I already entered here the material properties for POM, so 65 megapascal tensile strength and the shear strength divided by the tensile strength, so 55 divided by 65, 0.846. And now we can go down here and say, yeah, what's the thread length for 100 newtons, 2.15, and so on. I come back with the table. Here's the table for POM-C. So for 100 newtons, we need a 2.15 millimeter deep thread. Please note that at 2.16 millimeters, we get for 6060 aluminum 200 newtons, so almost twice as much, which makes sense because 6060 aluminum is in the two important parameters here almost twice as strong as POM-C. And then for 200 newtons 2.29 millimeters, 500 2.71 millimeters, yeah, and you see it's always almost double. 1000 newtons 3.42, 2000 newtons 4.84, 5000 newtons 9.10, and for 10,000 newtons, so a little bit more than a ton, the calculator told me, okay, my bolt cannot hold it, and it corrected that down to 9,660 newtons. That is what the weakest steel bolt can hold, and then we need a thread length of 15.7. So we should probably limit the forces on our bolts in POM-C, aluminum bolts, to at most 5,000 newtons with some safety factor involved, and have a minimum thread length of 9.1 millimeters. But what are the forces these bolts have to withstand, respectively, these threads here? So obviously not the pulling force, because yeah, that's taken up by the form of our bearing, but in theory we can push in the wheel too, and I measured here 10 kilograms or 100 newtons roughly. But that's probably not the problem. The problem arises when I push down here on the wheel and create a torque. And remember, I can push down here on the wheel. Yeah, we tested that with a whopping 210 newtons. And now we need some static calculations again. At its core, it's a lever problem again, like we had in the very beginning with the shaft in the bearing. The math is exactly the same, so but the geometry is a little bit different. So if I'm pulling down here with 210 newtons, I'm imparting a moment here on the whole assembly. And yeah, in my drawing, the top connection here would go into compression, so no problem. But at the same time, the bottom connection here, yeah, the force would try to pull it apart. So additional load would come on to this bolt here. Let's make a drawing. I know it looks a little bit funny, but believe me, it's a lever problem again. So the force here at the wheel is pulling down, and that creates a moment around our fulcrum. That is the top screw that goes into compression, so no problem there. And we have to counter this moment by a second force here, which is created by the bottom screw over that lever. Now, in static calculations, the form of the lever doesn't really matter. The only thing that matters is the distance between the force and then the perpendicular distance between the force and the fulcrum. So we can basically redraw that lever part at that dashed line here directly connected to our fulcrum, and that has incidentally a length. If you look at the drawing of 75 millimeters, our force is 210 millimeters, and now we have to counter that moment here by pulling on that lever arm here with a certain force generated by the screw, and that's just the distance between the two screws. So the force on our screw is equal to the distance to the wheel times the force at the wheel. That's the moment turning in that direction, and this is divided by the length of our second lever arm here, the distance between the screws. Let's make an Excel sheet. And here it is. So our down force on the wheel was 210 newtons, the distance to the wheel 75 millimeters, and I have here in 5 millimeter steps some realistic values for the distance I can create between the screws, and this gives us these forces at the screw. And in this column I simply multiplied the forces on the screws by a factor of 3. That's the usual safety factor for dynamic loads. And yeah, we have a dynamic load here. And you see, even at a small distance, like I've drawn it, of about 35 millimeters, the force on the screw is just 1,350 newtons. And if we go back to our little table here for M6 thread in POM-C, then you see we can easily accommodate that force with a thread length of, let's say, 4.5 millimeters. So no problem at all. I mean, I will probably go for more like 10 millimeter or 50 millimeter thread length. So we're safe. But what about the key? The key has to take up quite a lot of torque. We measured in the very first video 26.25 Newton meters of torque I can apply here. Fortunately, there is an online calculator for that too, and all we need to know is the, can I fit that here? The shear strength of our 6060 aluminum, which is 105 megapascals. And here it is. Link in the description as always. One remark, that's a calculator for ISO standardized keys. So sorry if you're living in Imperial land. Okay. So I entered our shaft diameter and 3 times, it's a dynamic load of our torque, that was 26.25 Newton meters. And then the maximal possible, according to ISO, key length for that shaft diameter. It says somewhere in the ISO the key length should be less than about 1.5 times the shaft diameter to ensure good load distribution. If you make your key just longer, other effects come into play, like the key having to take up the twisting from the torque in your shaft, and yeah, then this is all void and invalid. So ISO with that parameter gives us a key width and a key height of 4 millimeters. Then we have, of course, to make the key ways at a certain depth. And we have a shear force of 13.13 kilonewtons, and that gives us a shear stress on the key of over 180 megapascals. Remember, 6060 can only take 105 megapascals. We have a problem here. However, if we go to a shaft diameter of 12.1 millimeters, we have a 5 mm key, and shear stress is reduced to 144. That's still not ideal, but so we're not quite there at a safety factor of 3, which would be desirable normally. But maybe we can live with that. Or the other possibility, if we go back to 12 millimeters, we simply use 2 keys, one at the top and one at the bottom. Not something I really want to do, but it would be a solution here. So yeah, we have to really look out for that key. Short update, I came up with a solution. So if we take a 5 by 5 millimeter key with a length of 12.5 millimeters, the shear stress is 208 megapascals. If we take 2 such keys, but not on opposite sides, but in series, so to say, so on the same side, but with a little distance, we're fine. Then that pressure halves effectively, and we are below the 105 megapascals my 6060 aluminum can take. And in the drawing it would look something like that. We simply have here in our shaft to wheel adapter 2 keys with a little distance between them, each 12.5 millimeters long. Perfect. That leaves us just with the bolts here at the end, which also have to take up that torque I can apply here times 3 because it's a dynamic load. First, we have to calculate the force that is exerted on our 2 stop bolts here when they collide. And that's basically our measured moment, 26.25 Newton meters times 3, safety factor, it's a dynamic load. And that's divided, we already did that, by the distance of the bolt from the axis. Of course, I again made an Excel table, so here is our moment, and that's the distance of our bolt from our shaft between 15 and 30 millimeters, and that's the force exerted on the bolts when they actually, during the turning of the wheel, collide. And these are quite some hefty numbers. So 1560 millimeters, that's my current drawing. So about 5,000 newtons, or approximately 500 kilogram force. And that's linear. So if I lengthen the whole thing, go out to 30 millimeters, I basically halve the force. But yeah, I cannot make that lever as long as I want. It has to fit into the housing. So we somehow have to deal with these large forces. Now that we know the forces, we have to decide how to calculate the whole thing. So I don't want these bolts, these 2 colliding bolts as one rotates, to break. I want to limit their flex, that is, their bending. Yes, we're back to beam bending where we started. Okay, so the point where the 2 beams, my bolts, collide is about 3 millimeters plus the bolt diameter over 2 apart. So that's the effective length of our beam if we want to calculate beam bending. And as always, I want to limit the flex to 0.1 millimeter at maximum force. And now we can go back into our beam bending application. So here is our trusty beam bending calculator again, link in the description again. So we have the situation, we have here a firm clamping. Yeah, that's where the bolt goes either into the shaft or into the bearing itself, into the housing of the bearing. And then we have a little length here. We calculated that as half the bolt diameter. So for a 6mm bolt, that would be 3mm, plus 2mm of some soft material, plus 1mm gap. And that's 6mm. And I fiddled around here with the number or the strength of the force. I'm up to 6 kilonewtons here now, until I got for my 6mm round aluminum bolt a maximum deflection of 1/10 of a millimeter. So a 6mm bolt can easily take 6 kilonewtons, and that's beyond the largest force that was 5.2 kilonewtons we calculated in our Excel sheet. So we're golden here, but I do some more calculations anyway. So you already saw that first line here in the online calculator. So for a bolt diameter of 6mm, and so we have here a length, so 6 divided by 3 plus 2mm here for some rubber stuff and 1mm air gap. I had a maximum possible load at a maximum bend of 0.1mm of 6,000 newtons, which basically covered my absolute maximum force I'm expecting, with a safety factor of 3, so everything's fine. Just to be on the safe side and have some material to play with, I calculated the same for 8mm bolt. So 8 divided by 2, 4mm, plus my 3mm air gap and material. And that alone yielded, or could yield at 0.1mm bending, 12,000 newtons. So yeah, really massive. However, let's say I want to increase that gap here to 3mm. Let's say 3mm rubber plus 1mm air gap. So my distance here goes up to 7mm for a 6mm bolt. Then the force is already reduced to 4,000 newtons. Remember, the bending increases with the cube of the length, so length to the power of 3. And then I have already to look into that table and make sure that my lever here gets long enough. In that case, 4,000 newton, at least 20mm. The same happens, of course, again, if you take an 8mm bolt, then the length increases to 8mm and the load at 0.1mm bending decreases to 8,500 newtons, which is still within any value we calculated here. So I guess I have enough now to come up with a final drawing. And that's it for today. Next time, when we work on that special project here, and that might take a while because I need to source now all the materials, and maybe I will make some enhancement on my little mill. We will actually do some machining. I will show you the final drawing, maybe the first detailed drawing of some part, and we'll do some machining. In between, I might start another project. We'll see. Till then, bye.